Okay, let's talk about greatest common factor. So Unit 4, we're going to begin factoring polynomials. And to start this out, we're going to start really simple with just kind of some basics about getting the factors of different numbers. Now, the greatest common factor is, and that's what goes here, greatest common factor, or GCF, is the highest number or term that will divide into two or more terms evenly, so without a remainder and without getting decimals or fractions, so divide evenly. And one method you can use to find the GCF is a factor tree. Another method is hedging, and there's other methods as well. These are just two that we're going to talk about in these notes. And you don't have to use these methods to find the GCF. You can just think about it. You can make a list of factors. There's multiple ways to do it, but these are just two ways that I'm going to show that you can use if you need to. So first we'll look at a factor tree. So we want to find the GCF of 36 and 60. So the biggest number that divides evenly into 36 and 60. And again, if you can think about it for a minute and figure out the biggest number that goes into both of these, that's great. If you're not sure, you can use one of these methods. So a factor tree is just a way to find all the prime factors of a number. So let's start with 36. And now I can divide that by 2. 2 is an easy one to use. 36 is an even number, so you know it divides by 2. 36 divided by 2 is 18. And we can continue this process. Divide by 2, we get 9. Divide by 2 doesn't work, but 3 does. And now here are the prime factors of 36, 2, 2, 3, and 3. Now let's compare those to the factors of 60. That's 2 and 30, 2 and 15, and 2 doesn't work, but 3 does, and that gives us 5. And so what you want to do, once you make your factor tree, compare common prime factors. So they both have a 2, and they both have another 2, they both have a 3, and that's all they have in common, a 2, and a 3. And so to use that to find the GCF, just multiply those three numbers together. 2 times 2 times 3, and that equals 12. So 12 is the GCF of 36 and 60 because it's the biggest number that divides into those two numbers evenly. 12 times 3 is 36, and 12 times 5 is 60. Now a factor tree is a great method, but it does take up a little bit of space. And there's numbers you write down that maybe you don't really use. A very similar process that maybe is a little more compact is called hedging. It's pretty much the same thing, but it's just a different way of writing it. So again, we'll do 36 and 60, and this is how hedging works. So 36, and I can divide that by 2, so I'll draw a little bracket here, and that gives me 18. Divide by 2 again, that gives me 9, and I can do 3s. So it's pretty much the same process, it just looks different. And actually you write exactly the same amount of numbers, so it really just is about your preference, and maybe it's a little more streamlined. It's one row of numbers instead of trying to tree it out like this. In both of these methods, recommend you definitely just use the smallest prime numbers, because 36 and 60 obviously have multiple numbers we could divide by, but you want to keep it small. 2s, 3s, 5s, divide by prime numbers. So 2 and 30, 2 and 15, 3 and 5. And just like a factor tree, we're going to compare numbers they have in common and multiply those together. And we still get 12 because it's the same numbers. Okay, so these are two methods you can use to find the GCF of a set of numbers. You don't have to do this. If you can think of the biggest number, that's fine. Or let me give you an example of a different way you can use this idea in a little bit of faster way. We'll do that next. All right, for example A, let's find the GCF of these sets of expressions. We have 18 and 36. I want to think of the biggest number that goes into these. We'll tell you what, we'll do 36 first. And that's 2 times 18. We already knew that, right? And look what we have here. We have 18 and 18. So you know that there's no bigger number than 18 that goes into 18. And 18 also goes into 36. So 18 is our GCF there. So if you want to save some time and you're going to do factor trees or hedging, start with the bigger number, because you may end up seeing that the smaller number is a factor of the bigger one. Now, for example, B, let's say I want to save some time. I don't want to do the complete prime factorization of each one. If you know a number goes into all three of the numbers you have, or all the numbers you have, but you're not sure if it's the greatest common factor, you can start with that. So I know that 6 goes into each of these numbers. So I'm going to go ahead and divide them each by 6 and see where that gets me. So 18 gives me 3, 30 gives me 5, and 54 gives me 9. Well, I know that 3 and 5 are prime, so I can't go further than that on those. 54, I could break 9 down into 3 and 3, but because the other numbers gave me prime numbers when I divided by 6, I can stop there because that's as far as we can go. So the greatest common factor here is 6. So these are just some different strategies you can use to find the greatest common factor. You don't have to do it the same way I am. You can make a list of factors and come up with it on your own. I'm just trying to explain a few different ways that you can use a factor tree or hedging to save some time. Now, for hedging, say I got 12 and 40. Again, you can think of a large number that goes into both, or you can kind of save some space and do hedging at the same time for both of them. Don't recommend it if you have trouble writing neatly or keeping these separate, but it is definitely something you can do. So let's divide these by 2, and we get 6 and 20. Let's do it again. Keep them separate here. Let's divide by 2 again, and we get 3 and 10. Now I know I can't go further because 3 is prime. 10 I could divide more, but I can't for 3, so I can pretty much stop there. So you can use hedging in this way, and you know that they both have a 2, they both have a 2, so that's 2 times 2 equals 4. 4 is our GCF on this one. So that's one way that you can use this idea without doing the entire prime factorization for each number. You can go as far as you can with numbers they both have in common, and then stop when you reach the end of that. All right, example D, we've got 3 numbers here, 14, 20, and 35. You can also just think about it. I know 2 goes into 14 and 20, but it doesn't go into 35. I know 7 goes into 14 and 35, but not into 20. And that's pretty much it for 14. And we can confirm this with a factor tree or with hedging, but that's it for 14, can't go further. 20, we get 10, and then 2 and 5. 35, we get 5 and 7, and that's it there, those are prime. None of these numbers match up for all 3 in our list. The first 2 have a 2, but not the third. First and third have a 7, but not the middle. Second and third have a 5, but not the first one. So the prime factor here, the greatest common factor, is 1. There is no larger number that divides evenly into all 3 of these, so our GCF here is just 1. Okay, so that is how you find the GCF of a list of numbers, or at least a few strategies for how to come up with the GCF of a list of numbers without spending all the time to do complete prime factorization for each one. Now, if you have variables with exponents in the mix, might seem more challenging, but actually it's a little easier. So the GCF of a list of variables is just the smallest exponent on that common variable. So let's look at an example. The GCF of 17a squared and 34a cubed is what? Well, first look at the coefficients. We have 17 and 34. So the GCF of 17 and 34 is 17 because 17 is prime, and if you divide 34 by 2, you do get 17. So that is the biggest number they both have in common. Now for a, we see we have an a squared and an a to the third. So they both have a, so we can put a safely in our GCF. And then just choose the smallest number, the smallest exponent on all of your terms with a, and that's a 2. So I know I can evenly divide a cubed by a squared, so a squared is my GCF. Let's do that a few more times. So for example, a, we have 6x and 18. So first do the coefficients, do the large numbers. We have 6 and 18. Well, I know that 6 goes into 18 because 18 divided by 3 is 6. Right? So I know 6 is my GCF there. They both do not have an x, just the 6 does, so we can't use x in our GCF, and that's just it there. Example B. Look at the coefficients first. We have 2, 4, and 5. Well, 2 and 5 are both prime. 4 does break into 2 times 2, but this 5 is the problem there. So our GCF here is just 1. Now we can check the variables. They don't all have m, and they don't all have n, so we can't use either of those. This is the GCF here. They all have to have the same variable to use it in the GCF. All right, example C. Let's look at the coefficients, 3 and 15. Well, again, I know 3 goes into 15 because 15 is 3 times 5. So 3 is the GCF here. Now both of these terms have an x, and the smallest exponent present is 1, so that's the exponent I use in my GCF. So 3x is the GCF here, or 3x to the first if you want to put that. Example 12, coefficients first. We have 12, 16, or example D, 12, 16, and 20. Now I can think of a number that goes into all these. 4 goes into all these numbers. So if I divide them all by 4, just to check and make sure, that one's 3, this one's 4, this one's 5. So I can break down 4 more into 2 and 2, but 3 and 5 are both prime. So this 4 they all have in common. That's my GCF. And now looking across all these terms, they all have an x. X, x, x. So x goes in my GCF, and the smallest exponent present on x is a 1. So I can put that or just leave it as an x. And then for y, they do all have y, and the smallest exponent present, these 2, so just 2 is the exponent I will use there. I can divide those evenly. All these terms I can divide evenly by 4xy squared. So that's how the GCF works. If you have variables, if they all have the same variable, you can use it in your GCF and then choose the smallest exponent that's present across all your terms.